Welcome to this lecture of mixed signal IC design. In today's class, we'll continue discussion on the specifications of DAC. So in yesterday's class, we were looking at we started with DAC as a block, and we understood like the transfer care of the DAC. What do you mean by one LSB? The smallest possible change, the maximum analog output voltage that can be generated in a DAC, the relation between these, and resolution. These kind of general informations we have like we dealt yesterday, and we also solved one or two numericals based on that. How to find resolution of a DAC, how to find the accuracy and related stuff, right? So today we'll continue, and even though the details like resolution, the full scale voltage, all those things are also part of specification, but most what we'll be going to discuss will be based on two major categories we'll discuss today. So again, we'll start with DAC. Once the DAC is done, we'll look at the specifications of ADC in a bit detail after looking at the specifications of DAC. So as I was mentioning mentioning yesterday, if you want to use or if you want to design a data converter, it requires proper understanding of the specifications, right? So basically what you understand by specification is these set of values, or the specification gives the features and limits of the static and dynamic operation of a data converter, right? So in that line, what we can do is we can actually classify the specifications of DAC broadly into two. One set we call it as static specifications, and another category we call it as dynamic specifications, right? So apart from this, there are, if you look at the data sheet of any data converter, you will have n number of other details or information given. So we'll be limiting our study only to some of the static and some of the dynamic important some specifications. So this is how we can classify the specifications as static and dynamic. Now coming to the static specifications, yesterday in the case of DAC, we saw how the output how the characteristics of a DAC looks like, right? Like when your input digital word changes, how analog output voltage is generated, and we looked at the input output cara. So generally so when we talk about the static behavior of a DAC, so the static behavior of a DAC is given, or we can understand about the static behavior of DAC by looking at the input output cara. Input output cara is nothing but the transfer cara what we discussed yesterday for a DAC, right? Now if you remember in the static cara, when I was plotting input digital word D over here and analog output over here, when your input digital word changes, say for example 3-bit DAC, initially it was 000, then for 001 we'll have a 1 LSB change, then for 010 you have one more LSB change, right? This is how we have looked at the cara of the DAC, or this is how we looked at the input output cara of a DAC, right? So what we observed here is for every bit change, we could see that there is one LSB change, right? And if you look at this is actually, we can call it as one step, and this can be called as step height, right? So every step height for every input digital data change, the output, the reflection at the output will be one LSB change. That one LSB is actually equal to the step height, and this step height will be uniform, or should be uniform. Ideally the step height will be uniform. That means for every bit change at the input, output change by 1 LSB, and if you look at the cara of a DAC, for every bit change the transition will be for 1 LSB, and the step height will be uniform, right? So that is what we expect from a DAC, the input output cara. But if at all there are any deviations from this ideal cara, or this can be treated as an ideal cara of a DAC, and if at all any deviations from this ideal cara, so deviations from this ideal cara it could be the deviations can be because of n number of reasons. In a simple way, what we can say is some non-idealities can result in some deviations. So deviations from ideal Cara. Right. So if at all there are deviations from ideal Cara, that will lead to errors in DAC or ADC, because DAC or ADC, what they are doing is they are precisely converting digital data into analog or analog into digital data. So deviations from the ideal Cara will definitely result in some kind of errors, right, or some kind of distorted response. The output of the data converter may show some distorted response if there are deviations from the ideal Cara. Now, whenever there are deviations from the ideal Cara of a data converter, whether it is digital to analog or to analog to digital, those deviations are quantified. Those deviations, so deviations from ideal behavior. When I say ideal behavior, here what I meant is the ideal graph of the transfer Cara is what I am looking at. So whenever there is deviations from this ideal Cara, that will result into errors, and those errors are captured, or those errors are mainly quantified with the help of the static specifications, right? So deviations from ideal behavior are quantified under this heading static specifications, and the most important static specifications are one is called as DNL and other one is called as INL, where DNL corresponds to differential nonlinearity. We will look at these two deviations from the ideal behavior in detail: differential nonlinearity, and INL is called as integral nonlinearity. Right. So ideally a DAC or an ADC, ideal behavior, we know the ideal behavior for a DAC is for every input change there is one LSB change. That means for every bit change the step height should be uniform, but due to some reasons, it could be out of non-idealities, if at all there is a non-uniform step height, or if at all there are deviations from the ideal behavior, those things are, or those that will lead to errors or distorted response, and those things are quantified with the help of static specifications, and two important static specifications are DNL and INL, right? We'll look in detail what a DNL and INL is. Similarly, coming to the dynamic specifications, basically the frequency response, how a DAC, a data converter, will respond to different input frequency along with speed, the frequency response and speed. The frequency response and speed of most of the analog components. So this, when we say most of the analog components, the frequency response and speed actually determines the dynamic performance. So these two decides the dynamic performance. And here what all deviations are there, those things we quantify with the help of dynamic specifications. To list a few, we talk about signal to noise ratio. Here there are different forms we write. We write in terms of SINAD, we write as signal to SNDR, noise and distortion ratio. We talk about dynamic range here. Then we talk about effective number of bits called as ENOB, or we talk about SFDR, spurious free dynamic range. There are so many dynamic specifications listed for data converters. We look in detail some of these specifications. All right. So generally we can say that specifications of DAC can be classified into two. One is static and the one is dynamic. And now we will go ahead and see what is this static specifications, especially this differential nonlinearity. Are you guys with me? Can I get some response in the chat? All right. Fine. Coming back to this differential nonlinearity, that is one of the static characteristics of static specifications of DAC. We know how an ideal DAC responds. So we are talking DAC, differential nonlinearity with respect to a DAC. So let us take the example of a 3-bit DAC. Let me take the same graph what we had yesterday. One second. I don't know what's happening. Alright, yeah. So this is what we have looked at the characteristics of DAC yesterday. And here you can see that for every bit change, every change in digital input word, so this is your digital input word. For every change in digital input word, you can see that there is one LSB change, and what we are expecting is always that this step height will be uniform. The step height will be uniform. This is what we expect in a ideal DAC, right? So as I mentioned here, as we just explained, there could be deviations from this ideal behavior. So that can be due to the non-ideal components, because we are not working with ideal components. We all work with in a real circuitry, we work with non-ideal components, and these non-ideal components can cause the increments. No, there for every input digital data, analog voltage should get increment by 1 LSB, right? So these non-ideal components can cause the analog increments to differ from their ideal step height. Let me just write the definition here. Analog increments to differ from their ideal values, right? The ideal value is always 1 LSB. Now for one bit change, say what we are expecting is 1 LSB change. Now say for example the bit change is happening from 011 to 100, and what we are expecting is 1 LSB change here, right? So instead of 1 LSB, the non-idealities in the components can make this change more than 1 LSB, or it can be less than 1 LSB, right? It is not like any specific value, but depending on the non-idealities present in the circuit, the change can be more or less than 1 LSB. And if at all it happens, if at all if the difference is if at all the change is not 1 LSB, that means there is the analog increments is not happening in a uniform way, and that is deviating from the ideal value, and that result in this error, right? So in order to quantify that, or in order to say that okay, this DAC is having this much error, what we do is we have this performance metric, we call it as differential nonlinearity. And how we characterize this is the difference between, so for every bit change there is a difference from the ideal expected is 1 LSB. We will see for every bit change what is the actual height, actual step height, and what is ideal step height, and that difference we will quantify as differential nonlinearity. So the difference between the ideal and non-ideal values. So when I say ideal and non-ideal values, in the case of DAC, it is the step height. The difference between ideal and non-ideal values, that is step height, is called as DNL, is called as differential nonlinearity, right? So if I want to write in the form of an equation, I can say differential nonlinearity corresponding to the nth input bit transition, I can write the differential nonlinearity as the actual increment height of the step, actual increment height minus the ideal increment height. So ideal increment height is always 1 LSB. So actual increment height minus ideal increment height is considered as the DNL or the differential nonlinearity for that specific bit change, that specific input transition. All right. So I hope you are with me. Can I get some response? Are you guys with me? Yeah. So we have, when you for any DAC you can get the characteristics. You can compare the Cara with the ideal Cara. When I say ideal Cara, for every bit change 1 LSB is what we need to look for. So what does this DNL gives, or what is the implication of this DNL, or when you have the DNL value, what does it say about a DAC? What do you think? So we quantified this error or this difference as differential nonlinearity corresponding to every bit. So what does this DNL tells about this DAC? By looking at the DNL value, what can you infer about a DAC? Yeah, it is accuracy. Definitely it is accuracy. Yeah, we can say it is accuracy. In a more precise way, I can say DNL measures how well a DAC can generate uniform analog LSB multiples at its output, right? So because for every change what I need is 1 LSB. So how well a DAC can generate output in terms of multiples of LSB, that is what DNL measures, right? So let me write it over here. DNL indicates how well a DAC can generate uniform analog LSB multiples. So output can be 1 LSB, 2 LSB in that way, because generating from first, it will be 1 LSB will be keep on increasing, right? So multiples at its output. So DNL is a measure of that, how accurately DAC can generate multiples of 1 LSBs at the output. Alright, so just to have a better understanding, let us take one simple example. I have a simple example over here. So you can see that the question here is determine the DNL, differential nonlinearity, for a 3 bit given that the DAC is non-ideal, right? So the moment you hear that the DAC is non-ideal, you can conclude that yes, there are some deviations from the ideal behavior. The transfer curve is given. It is also given that the reference voltage is 5 volt, right? Now if you look at the characteristics here, if you look at the Cara, we know that for 0 0 0 input we are not expecting any output, right? The output should be 0. Now for let me write it here. This is 0, this is 1, 2, 3, 4, 5, 6 and 7, right? So for every input digital word transition, what we are expecting is a 1 step ahead or 1 LSB increment. You see here it is marked as, this is 1 LSB, so this is 1 LSB height, so it is marked as ideal height. This is also marked as ideal height, but here the transition from 2 to 3, when the input the bit change from here 0 to 1, this transition happens. Whenever this transition happens, this height is more than 1 LSB and it is marked as 1.5 times ideal height. So ideal height can be considered as 1 LSB. So 1.5 times ideal height is 1.5 LSB. So this is 1.5 LSB. Now again you can see from 011 to 100, here also there is another change. What we are expecting is 1 LSB, but this non-ideal DAC is giving only half, the change is only 0.5 times LSB, right? Now again from 100 to 101, you can see that the transition is only 0.25 LSB, right? So let me write it as 0.25 LSB. And then from 101 to 110, you can see that the height is more than expected, which is 1.75 LSB. And finally from 110 to 111, it has come back to 1 LSB height. right? Now, in the graph you can see a dotted line. So the dotted line is something what we are expecting as ideal. So this is actually the ideal graph or the ideal behavior. Now you can see that some of the points are outside the ideal behavior or the ideal slope. So this is outside. Now even though this is inside, no, but this is not giving you the actual step height. This is away. So you can see that there are deviations from the ideal behavior, and if you want to quantify this error, we take the help of this differential nonlinearity. And how we do that? So DNL is measured for every input transition change, right? So what we have to do is we have to write for DNL 0, DNL for the transition 1, DNL 2, DNL 3, DNL 4, DNL 5, DNL 6 and DNL 7. This is what we need to write. Now, so there are different ways. So whenever you approach a numerical, you can write in different ways. In this case, it is given as ideal height. Actually, that can be that will be given in terms of LSB, or you can actually find the LSB value also. So what is one LSB value in this case? What is LSB of a DAC? Or for a 3-bit DAC, what is LSB value for this? Any response from in the chat box? 0.125, is it 0.125? Yeah, so VREF. So one LSB value is nothing but, what is one LSB? VREF divided by 2 to the power of n. 1 LSB is VREF divided by 2 to the power of n. This is 5 divided by 8. 2 to the power of n is 2 cube, which is 8. So what is 5 by 8? Either you can represent in terms of fraction, or you can write in terms of decimals. Yeah, so this is 1 LSB value, and yeah, it is 0.625. 0.625 volt is 1 LSB, right? Now what we can do is we can calculate the DNL for every bit, right? So let us first look at the first input digital code 000, and we know that for when the input digital word is 000, we are not expecting any increment at the output, right? So generally we will not write DNL for the first or for 0, because for 0 we are not expecting any transition, right? So DNL 0, we generally will not specifically mention about DNL because there is no increment for digital word 000, right? Now for DNL 1, how will you write for DNL 1? So what is DNL 1? DNL 1 is for the input digital word 001, the actual height minus ideal height. What is actual height? Actual height is 1 LSB, ideal height is also 1 LSB. So DNL of 1 is 0. Right. Now what about DNL 2? For DNL 2, is there any change? DNL 2 also, you can see that from the behavior, even though the DAC is non-ideal, for the input word 2, the transition is equal to the 1 LSB. So DNL 2 is also equal to 0. So what is DNL 3? For DNL 3, the actual height is up to 1.5 LSB. So actual height is 1.5 LSB. So I should write 1.5 LSB minus ideal height. Ideal height is 1 LSB. So this is equal to 0.5 LSB. 0.5 LSB is the DNL for third input bit transition. Now what about DNL 4? DNL 4 is 0.5 LSB is the actual height. So 0.5 LSB minus 1 LSB, which is equal to minus 0.5 LSB. This is the DNL for the fourth input digital word. Now for 5, the height is only 0.25. So DNL 5 is equal to 0.25 LSB minus 1 LSB, which is equal to minus 0.75 LSB. Right. And now looking for DNL 6, 6, you can see that the height is around 1.6 is 1.75 LSB minus 1 LSB, which is equal to 0.75 LSB. And finally for DNL 7, the actual height is 1 LSB and ideal height is also 1 LSB. So that will result in 0. DNL of 7 is equal to 0. Right. So for any DAC, given the behavior of a DAC, either in the form of a waveform or in the form of a table where you have values for you have actual increment and ideal increment values, you can find DNL by for every input digital code transition you have to write DNL, actual increment height minus ideal increment, and for input digital word of 0 0 0 there is no increment expected, right? So this is how we write DNL for a DAC. Now one more thing what we generally do is, once your DNL is available, we'll also so once the DNL is available, we generally do a plot of DNL. Now the idea is not just to have a plot, the idea is to have careful look at the value of DNL. So what we generally do is, after getting the values, by the way, any doubt in the DNL calculation? Can I get some response in the chat? In terms of LSBs we can write, and this is digital input word. Alright, so now generally what we do is, after getting the DNL values, we will plot 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and this is 1 1 1, right? And on the y axis this is 0 0 LSB, and this is maybe 0.25 LSB, 0.5 LSB, 0.75 LSB, and 1 LSB. This is one. Similarly, we can mark here as well, minus 0.25, minus 0.5, minus 0.75, and minus 1, right? So in our case, we have the DNL values, right? For 0 it is 0, let me just plot it. 1 it is 0, so here is the first point, second point. For 2 also it is 0. For 3 it is 0.5 LSB, so it is 0.5 LSB. Now for 4 it is minus 0.5 LSB, so it is somewhere here. Then for 5 it is minus 0.75 LSB, which is somewhere here. Then 6 it is 0.75 LSB, is close to this value, and 7 it is 0 LSB, right? So generally we'll have a plot like this, which shows the variation of DNL right, and even from the table itself we can analyze, but this is a regular practice to plot it, and we'll always see that, or generally for a DAC, to be n bit accurate, it is considered that the maximum DNL for an n bit accurate DAC is considered as plus or minus half of LSB. So an LSB, the maximum DNL which is allowed for any DAC is maximum up to plus 0.5 LSB or minus 0.5 LSB, not more than that, right? So in this specific example, you can see that even your DNL is exceeding this value, but this is generally considered as a standard value where we keep DNL max as plus or minus 0.5 LSB, right? Now let me ask this question. So say for example, you are getting a DNL value for a specific bit as so for x bit, x input code, you are getting DNL as say -1. So what is the meaning of that? If you are getting DNL as -1 LSB, what is the meaning? Yeah, it is inaccurate. That is true. Offset by 1 bit, no rise, error in 1 bit. Yes, true. So look at this, no? Your DNL will get -1 LSB when you have a value, when your actual increment is 0. When there is no actual increment only, you will get a DNL value of -1 LSB, right? So let me write it here. Yeah. So when you write DNL for any bits, the actual, yeah, we know that. So the actual is 0, then only when we subtract from your 1 LSB value, you will get your DNL value as 1 LSB, right? So the meaning of this is, for that particular input digital code word, there is no transition itself, right? Or we can say that whenever this condition arises, we say that the DAC is not monotonic. So generally we say that monotonicity is something which is required for a DAC. For every increment at the input, there should be a corresponding change at the output. But whenever your DNL value is equal to -1 LSB, we say that the DAC is non-monotonic. That means the DAC is not responding for 1 bit change at the input, right? So this is something very important for a DAC with respect to when your DNL is -1 LSB, the meaning is the DAC is non-monotonic. And this is also important, the maximum DNL allowed in a DAC is around plus or minus half of LSB, or this can be further written as, we know that 1 LSB value is Vref divided by 2 to the power of n, right? Now when this is half of LSB, this will be multiplied by 1 by 2, right? Or I can also write this as DNL max can be written as Vref divided by 2 to the power of n plus 1. This is just another way of representing maximum DNL is half of LSB. Alright. So this is about DNL, and if you have any questions, you can ask. Let me answer that.